Hello everyone. In today's lecture, we will discretize diffusion equation using finite volume method. So, first we will consider steady diffusion equation for a general variable phi with a source term, and we will use finite volume method to discretize this equation. So, let us write the governing equation. So, steady diffusion equation so we can write divergence of gamma grad phi plus S is equal to 0. Okay. So, S is the source term, maybe heat generation in case of heat conduction equation, and gamma is diffusion coefficient. So, it is K thermal conductivity for heat conduction equation. So, now we have written this equation for any general variable phi. So, phi is any general variable, and this is the volume control volume we will use. So, you can see this is the capital P, okay, and this is the cell center of this main control volume, and the neighbor control volumes are in each direction, it is capital E. So, that is the cell center of neighbor control volume. Similarly, capital N north, W west and south, and the phase center. So, as we have considered two dimensional grid, so for this particular cell we have 4 phases. So, one is small e, that is the phase center, then small n phase center of the north face, small w is the west face, and small s is the south phase center. So, we will now integrate this equation over this control volume. So, that is the main control volume. So, in the main control volume we will integrate it. Okay. So, now let us define a flux vector J which is represented as minus gamma grad phi. So, we will introduce a flux vector, okay, that is denoted as J as minus gamma grad phi. Okay. So, sometime it is known as diffusion flux vector because we have considered a diffusion equation. So, J is minus gamma grad phi. So, obviously J in 2 dimension you can write J x I plus J y j. Okay. So, if you put it in this equation, then what you will get? So, you will get minus divergence of J plus S equal to 0, or divergence of J is equal to S. In this form we have written, so that in general form we can integrate it, and we have written in the divergence form. So, now let us integrate this equation over this control volume. So, integrate the above equation over the main control volume. Okay. So, we will integrate it. So, volume divergence of J dV is equal to volume integral of the source term into dV. So, now for the flux vector, this integral will convert volume integral to surface integral using Gauss divergence theorem. So, using Gauss divergence theorem, this integral you convert into surface integral. Okay. So, it will be j dot ds is equal to volume integral s dv. So, you can see that up to this point during the integration we have not made any assumptions, but now we have to make some assumptions because j we have to integrate over the faces, okay, of the control volume. So, but at each point the value of j is not known. So, we will use some assumptions. So, first assumptions is that j varies linearly along the faces. Okay. So, we will first assume that whatever j is the flux vector that varies linearly over the faces, and the second assumption is that the mean value of this j will take at the face center small e, okay, for the east face. So, the assumptions are, we assume that j varies linearly over each face of the cell P, so that it may be represented as by its value at the face centered. Okay. And for this source term also we will take the mean value, and we will assume that the mean value of this source term S over the contour volume is S bar. Okay. So, obviously you can see that if we are taking the mean value at the either cell center for this volume integral and the face center for this surface integral, so both will give the second order accuracy. So, let us write that this your j dot ds, so that is equal to integral s dv, this is your volume integral, it is area integral. So, this j now you need to integrate over these faces. So, now we will take the mean value at this face E, north, west and south, all these 4 faces. So, now we can write it as j e dot ac plus j w dot s w plus j n dot s n plus j s dot s s is equal to, now this s is the source term and average source term we will take into delta v. Okay. So, obviously you can see in this case what is delta v? Delta v is your main control volume is P, and for that we have delta x and delta y. So, it will be delta x into delta y. Okay. And the surface area AC, okay, will be your AEI, okay, where AE obviously for this east face you can see. So, this is your delta y. So, A is delta y, but as we discussed HW will be minus AW I y, because for this face the outward normal is in the negative x direction, right. So, this if this is your x and this is your y, then it is always we take the surface normal outside. Okay. So, obviously it is in negative x direction. So, you will get minus AWI and AW is your delta y. Similarly, Sn is equal to Anj, where An is equal to, you can see this is your delta x and Ss is your minus AS, similarly because your normal is in the negative y direction. So, minus ASJ and AS is your delta x. Okay. So, we know the volume as well as the surface area vector for each faces. Now, let us make the dot product with j. So, what is j? So, j already we have defined as minus gamma into grad phi. Okay. So, now this we have to make the dot product with the surface vector. So, for the first term let us first write. Okay. So, j e dot a c. Okay. So, j e this you can write minus gamma grad phi at east dot a c. Okay. A c is A e is the magnitude of the surface vector. So, that is nothing but delta y in this case, and this is your unit vector in the x direction, that is I. Okay. So, now you know grad phi for this two dimensional case, it is del phi by del x I plus del phi by del y j. Okay. So, now if you make the dot product, okay, so you will have only AC in only unit vector I. So, this I if you make the dot product, so I dot I will be 1 and j dot I will be 0. So, obviously I dot I is 1. So, del phi by del x will remain. So, you can write minus gamma e a e, okay, and we can write del phi by del x. Okay. This gradient you have to find at the face center E. Okay. So, now you can see gamma may be constant, then gamma will be uniform, but now in this case in general way we have written that at east face gamma. So, if your diffusion coefficient is varying, then you can have the different values at different faces, but if it is constant it will be the same value. And this del phi by del x at each face now you have to find. So, del phi by del x is the gradient you have to find at the face center E. So, now again we have to make assumptions. Okay. So, we will assume that the phi, the value of phi varies linearly between the cell centroids. Okay. So, if it is linear, then you can take the derivative and easily you can find between the two cell centers, one is neighbor E and the main cell center P. So, now we will assume that phi varies linearly between cell centroids. Okay. So, now you can write J E dot S E is equal to minus gamma E A E. Now, you see del phi by del x at this face center E you need to find. So, the gradient at this face E. So, del phi by del x if you take, then it will be just second order if you use phi E minus phi P divided by the distance delta x e. So, the distance between these two cell centers is delta x e. Similarly, the between the P and W it is delta x w, and the cell center distance between north and P. So, it will be delta y n, and it will be P and S, it is delta y s. So, we have written this terminology in for a non-uniform grid. So, if it is a uniform grid, then obviously delta x will be delta x w is equal to delta x e. So, now del phi by del x, now we will write phi e minus phi p divided by delta x e. Okay. And you know that the order of accuracy of this discretization is second order accurate. So, now you can write as minus gamma e a e by delta x e phi e minus phi p. Okay. So, now you can denote this term as some coefficient d. So, you can write d at phase E. So, it is phi e minus phi p. Okay. So, that means your d is gamma e a e by delta x e. So, you see A is nothing but delta y for this particular case, because A is the surface area of this east face. So, that is your delta y. Okay. Now, similarly you discretize for the other faces. Okay. So, you can write j w dot s w. Okay. So, now it will be minus gamma w a w. So, at this face, this is your west face. So, if you are taking del phi by del x at this face center w, then it will be phi p minus phi w divided by delta x w. Okay. So, this is also second order accurate. So, phi p minus phi w divided by delta x w, and this you can write as minus d w phi p minus phi w. Okay. So, d w is gamma w a w divided by delta x w. So, j w dot s w. So, what is s w? S w is minus a w I, okay, minus a w I, and j w is your, this is the gradient. So, obviously, if you take the dot product, so you will only del phi by del x will remain, but with a minus sign. So, this minus sign and this minus sign will become plus. So, it will be gamma w a w, because surface vector is negative and the flux vector is one negative is there. So, it will become plus and del phi by del x. Okay. So, del phi by del x. So, del phi by del x at east face how will determine? So, del phi by del x it will be phi p minus phi w divided by delta x w. So, it will be phi p minus phi w divided by delta x w. So, it will be gamma w a w by delta x w phi p minus phi w, and it will be d w phi w phi p minus phi w, okay, and d w will be gamma w a w by delta x w. Similarly, for the north face you do. So, north face, okay, so north face area is n j, and now j dot j will be 1, okay, and I dot j will be 0. So, this only del phi by del y will remain. So, del phi by del y will remain. So, you will get gamma n a n with a negative sign, because this j is minus, and now del phi by del y. So, del phi by del y at this face center n. So, it will be phi n minus phi p divided by the distance between these cell centers, that is delta y n. So, it will be phi n minus phi p divided by delta y n. Okay. So, you can write minus gamma n a n by delta y n. So, it will be phi n minus phi p, and this with this diffusion coefficient you can write d n phi n minus phi p, where d n is gamma n a n by delta y n. Okay. In this case delta y n is delta x, and similarly j s dot s s. Okay. So, now you can see s s is negative and j is negative. So, negative positive gamma s a s, and only del phi by del y will remain, because j dot j will be 1, and del phi by del y at this face center if you determine. So, it will be phi p minus phi s divided by delta y s. Okay. So, it will be phi p minus phi s divided by delta y s. So, it will be gamma s a s divided by delta y s phi p minus phi s. So, it will be d s phi p minus phi s, where d s is gamma s a s by delta y s. Okay. So, now all the flux vectors with the dot product with the surface vector we have determined. Now, you put together. So, what you will get? So, it is your J E dot A C plus J W dot S W plus J N dot S N plus J S dot S S, okay, equal to S bar is the average value of the source term into delta V, and sometime this in compact form also you can write summation of J F dot S F. Okay. So, J F dot S F, F is the phase. Okay. So, phase is east, west, north, south, okay, is equal to S bar delta V. Okay. Sometime in compact form you can write this way. Now, put all these values. So, what is J E dot A C? This is minus D E phi E minus phi P, okay, plus D W phi P minus phi W, okay, plus minus D N phi N minus phi P plus D S phi P minus phi S is equal to S bar delta B. Okay. So, what we will do now? All the coefficient of phi p will put together and will keep in the left hand side, rest all other terms will take in the right hand side. So, if you take only the phi p, so you can see this is your phi p, this is your phi p, phi p, phi p. So, all this you take in the left hand side. Okay. So, what will be the coefficients? So, that you see minus minus plus, so it will be d e here plus d w, this is your plus d n and this is your plus d s, okay, into phi p. So, this is your left hand side and right hand side. Now, this east, okay. So, if you take in the right hand side, it will be d e phi e, then this is a minus d w phi w. So, it will be plus d w phi w, this is your plus d n phi n, okay, plus d s phi s, plus you have the source term S bar delta V. Okay. So, now you can see that the coefficient of the neighbors, you can see the coefficient of phi e is your d e and the phi w d w, phi n d n and phi s d s. So, these will represent at the coefficient a. Okay. So, a east will be d e, then a w is d w and a north d n and a south as d s. Okay. So, you can see if we represent this coefficient as a e, a w, n and a s, left hand side if we represent as a p, okay, the coefficient of phi p is a p is d e plus d w plus d n plus d s, which is nothing but a e plus a w plus a n plus a s. So, for this particular discretization you can see the diagonal coefficient, okay, is a p and that is equal to summation of all the coefficients, summation of all the neighbor coefficients. Okay. That means a e plus a w plus a n plus a s. So, phi p is the summation of all neighbor coefficients. So, that you can sometime write A p is equal to summation of A n b, where neighbor. So, neighbor is east, west, north, south, and now this equation you can write as A p phi p is equal to A e phi e plus A w phi w plus A n phi n plus A s phi s plus s bar delta b. Okay. So, this equation in compact form it is written as A p phi p is equal to summation of all the neighbors A n b phi n b plus b, okay, where b is your source term. In this case it is s bar delta b. Okay. So, now you can see this is the final discretized equation using finite volume method. So, obviously P represents I j, right. So, P represents I j, capital E is I plus 1 j. So, if you write the compass notation, okay. So, phi p is phi I j, phi E is phi I plus 1 j, phi W is phi I minus 1 j, phi n is phi I j plus 1, and phi s is phi I j minus 1. Okay. So, now you need to solve this discretized equation using suitable solver, and in finite volume method generally we will write in this A p phi p form, okay, where phi p denotes phi I j. So, in today's lecture we considered a steady diffusion equation, and we introduced one flux vector which is j is equal to minus gamma grad phi, and integrated the governing equation over the main control volume, and then we converted the volume integral to surface integral using Gauss divergence theorem. Then we have written the fluxes at the faces. So, now fluxes at the faces we have determined using two assumptions. First assumption is that j varies linearly over the faces, and second assumption is that we take the mean value at the face center of the corresponding faces. So, obviously this gives the second order accuracy. Then we have written the dot product of the flux vector and the surface vector, and there one gradient comes at the each faces, and those gradient again to calculate those gradient we assumed that phi varies linearly between cell centroids, and we could find the derivative of phi with respect to x and y, which is second order accurate. And finally, we have written the discretized equation in A p phi p form, where A p phi p is equal to summation of A n b phi n b plus b, where b is the source term s delta b. So, you can see that whatever assumptions we have taken, okay, so that leads to second order accuracy. Okay. So, already we have shown that the mean value theorem gives you the second order accuracy. Thank you.